In this next video, we'll talk about relay logic, and we'll just kind of look at a brief overview of relay logic. We've learned, about the discrete inputs and discrete outputs, and that's about what we need to know as far as creating a relay logic diagram is typically these discrete input and discrete output devices. So we'll look at, so when I say relay logic diagram here, this could imply one of two things. One, it can imply a physically wired control system, no PLC at all involved in it. It could also refer to the PLC program itself. We'll call that a lot of times a ladder logic diagram or a ladder diagram, and it's really the same thing. It's just that if we were going to hardwire all the devices physically with no PLC controlling it, then we typically would call that a relay logic diagram. And if it was programmed in a PLC, it would be a ladder diagram. But the way how it's designed, the way how it's kind of built, shall we say, is kind of pretty much identical. So this example is technically a relay logic diagram. So it would be as if we were hardwiring this for real in the real world. And we'll discuss that first because it makes more sense to understand how that's done before we really get into the programming. But all the whole idea of the PLC was was taking this that was hardwired, in the control panel and converting it into a program that looked exactly like this. And once it's into a computer and programmable, then we can quickly and easily make changes to it on the fly, unlike a hardwired system, which would take some work to actually rewire it if we had to make changes. But let's understand how we read this diagram. So we typically, again, we refer to this as relay logic, but you can also see it as a ladder. And the reason why they call it ladder is because it kind of looks like a ladder. We have our two kind of rails of the ladder and then our rungs of the ladder. So each one of these lines, we'll call it as a rung. And then these are kind of our rails. And we typically have a positive rail and a negative rail. So the positive, and this is referring to voltage, of course. So if it's 120 volt AC is our control power, then this would be our 120 volt AC line side. Basically, shall we say the positive, we typically call it the line side. And this would be the neutral. So our power flow typically goes from the line to the neutral. So our line side comes in, it would flow through this rung. And if we had a complete path here, it flows to the neutral and then back. And that completes our circuit. If it was 24 volt DC, then typically we refer to that as a positive and a negative. So this would be the plus or the positive 24 volt DC, and this would be the negative 24 volt DC. So first thing to always know and understand when you start looking at this is understanding the control voltage, and if it's 120 AC or 24 volt DC. So let's just say, for example, that it's 120 volt AC. We'll stick with AC here. So this again is our line side. So this would be the black wire if you're used to kind of how things are wired in your house. This week maybe consider the black wire, and this is the white wire. So the line and the neutral. And we know we don't touch the two wires together ever, because will cause a short. But in this case, we're flowing our line side down this rail, and then we're tapping off the rail in multiple places to go through the rung. And we kind of look at it as just kind of flowing rung 1, 2, 3. So we kind of, if we were going to analyze this diagram, we would start here at rung 1, and we would kind of come off of here, and we see that we have a push button. And we have it drawn as a normally open push button, which means that there is not a path through this push button. This push button is not passing power, another term for that. This is a normally open contact. So assuming that it is in the shelf state or off state, this is an open circuit, and there is no path to get from here to here to come across and energize this output device, which we recognize as being a relay. The circle means relay. CR1 would most likely refer to control relay 1. So we kind of name it, right? So CR for control relay, and 1 is just the actual identifier, because we can have multiple relays in this system. So this is CR1. So if we had a path, we would come through the coil, it energizes the coil inside the relay, and then it would flow out to the neutral and complete the circuit. That way we have our actual current flow from left to right. So we don't have a path here, right? So we come to rung 1, we come here, and we're at a dead end because this push button is not pushed down. So we have a dead end. So we come down to the next rung in the circuit, and we have a normally open contact. This normally open contact is labeled CR1.1. That refers to CR1, and dot 1 refers to the first contact. So I can see already on rung 3 that we have a dot 2. So that means that this relay is most likely a two-pole relay. We have one contact and two contacts, possibly. Could also maybe be using the form C version of the relay here, but being that it's labeled as dot 1 and dot 2 makes it sound like it could be contact 1, contact 2. So anyway, so we come to rung 2, we come up to this first device. It's a normally open contact, which means that if this relay is not energized, then this is open. So we're at a dead end here as well. So we kind of come on down to the next rung, rung 3. We come to this device, again, CR1.2, that means it refers to CR1, and this is a normally closed contact, which means that when this relay is not energized, this contact is closed and is actually passing power. So right now, the current is coming on rung 3, it's coming through this contact, but it's closed, and it'll come to this green LED indicator and complete the circuit. So that means the green light will be on. So basically, push button's open, red light is off, green light is on. Real simple. So I actually had that kind of animated here in the red lines. So the red lines would indicate, the power flow or the current. So we got a dead end, and then here we got a complete path, and the green light is showing as green. Now what happens when I push this push button? When I push the push button down, I now have a continuous path to CR1. So that means that CR1 will now energize. This power will flow across, or current will flow through this push button contact now and come to the relay, and that will make the relay turn on. When the relay turns on, CR1.1, normally open contact, will now close. This contact will now close and pass power through it. CR1.2, which is normally closed, will now open because it changes its state. And again, the states are either on or off. So if the state is on and then it changes its state, it goes to off, which means that the green light will no longer be on and the red light will now turn on. And that is represented in this next kind of picture. So the red line is now showing current flow through the push button to the relay, and now through the CR1.1 to the red, and the CR1.2 is now physically open. Now, this drawing it this way, doing this, so we changed this picture, changed it to now shows this normally closed and this is normally open. That's not really a good representation. We have to just use our we just have to kind of use our imagination and know that this contact is now energized and this contact is now open. We would not necessarily change its representation on a drawing this way, because we always want to represent on a drawing what the shelf state is. Once again, what the shelf state or unpowered state is. So we would not want to change this on a drawing, right? We would keep this normally open, but for illustrative purposes, they're showing this contact is now closed and basically passing power. It changes state from off to on, and this one changes state from on to off. So that was an easy example. Here's a little bit more detailed example, perhaps, that would actually show the source of the power coming in even. So in this case, we have a 480 volt AC power feeding um, this control panel, but we would not use 480 volts AC as our control voltage. Remember, we're going to use typically 120 volt AC and 24 volt DC. And the reason for that is because those would be really deemed safe voltage levels. 480 volts AC would be way too high of a voltage level for doing control, especially control that we might actually come in contact with. We might actually be pushing some kind of push button or turning some kind of switch, and we don't want 480 volts sitting on the back of that push button. So we want to keep it at a safer 120 volt AC. So we use what's called a control power transformer. This is nothing more than a transformer that takes the 480 volt power in and steps it down to 120 volt AC. So once we get to 120 volt AC, we have our line and our neutral. So we got here's our complete circuit flowing from, we're going to go kind of counterclockwise here. We're going to kind of go this way, and then we'll kind of assess each rung, and then we'll have get to complete the circuit back. So in this case, we have a master power control switch, right? A switch symbol indicating, go into an indicator lamp. So when we turn our master power control on, we'll have a light telling us that our system's on. Also, when we turn the master control power on, we'll come through a heater. We have kind of a parallel branch here that has a heater on switch. So if the master control power switch is on and if the heater switch is on, then the heater will turn on. But the indicator light will always be on as long as this switch is closed, right? So if this switch is closed, it goes straight across, light on. But when this switch is closed and if the heater switch is on, then the heater will turn on. Next rung down is the high pressure switch. So if the high pressure switch closes, then we're going to energize the relief solenoid. So if we had a high pressure in the line, we'll open up this relief solenoid, which would bleed off some pressure. I would kind of make that assumption from just the terminology here. Next rung is a float switch. So now we're looking at some kind of level in a level in a tank or vessel or reservoir or something. So when the float switch is normally closed, so that means that this CR1 is pretty much always energized unless this float switch opens. So if there's a liquid level high enough, then the float switch will open. When the float switch opens, then CR1 will de-energize. So the float switch is normally closed. The relay is normally operated as a result on. This contact here means it's closed because this CR1 is energized. Therefore, this normally open contact will change its state from off to on, which indicates that this indicator lamp is always on. As long as this float switch is kind of in this normally closed state, this lamp will be on. When this float switch opens, this drops, and of course the light no longer turns on. All right, so these diagrams are not that hard to interpret. It just, again, helps to understand the symbols or the symbology. Once you understand the symbols, you can start to understand, what the functions of each of these are. Just, of course, these things are also, luckily, they were nice enough to document, which is also a very good practice to document what these, just because it's a switch, we don't necessarily know what the switch is. So it's good to document that it's the master power control switch. So we can make some assumptions just looking at the schematic with really not even knowing almost anything about what this application is. We know there's some kind of master control switch, which we have to have on. If the heater needs to be on, we know that there's some kind of high pressure switch and a relief. So obviously we're worried about a high pressure possibly. And then we also know there's some kind of float switch. So we know there's some kind of level indicator out there, level switch out there, and we have a visual indicator to the operator that the tank is either, at the right level or not. So we can make those assumptions just based on these few rungs in this relay logic diagram. So this is exactly what we'll be doing throughout this class. We'll be kind of taking basically these little control scenarios, just like we kind of see here, but putting it into program form in the PLC versus actually hardwiring it as this would probably be based on this schematic. And that's it for this video, and we'll pick up next with a video on discrete I/O handling for the PLC.